students in the class, so I think we may need to wait few more minutes for the students to enter into the class, and then we can start our chapter, that is strain transformation. Today we will study the, you can say, the introduction about this subject, about this topic, and we will also derive the equations for the computation of transformed normal and shear strain. While we are waiting, tomorrow we have what you say, OBE visit. Okay, so we may need to reschedule tomorrow's class. So Uzair,
yes sir.
If I see tomorrow's schedule, आप हैं जी सेक्शन है आपका बी, आपका लेक्चर है 11 से 12, नहीं सॉरी 10 से 11, 10 to 11. Yeah?
Yes sir.
दस से 11 तो प्रेजेंटेशन में आप ब्रेक के बाद फ्री हैं?
सर ब्रेक के बाद प्रोफेशनल एथिक्स का लेक्चर है,
5वां है ना? 5वां लेक्चर होता है कितने बजे? 5वां लेक्चर होता है, ये होता है 1 से 2।
सर 1 से 2।
ठीक है, अगर हम अपनी क्लास अरेंज कर लें 2 से 3।
ठीक है सर, कर लेंगे।
2 to 3, ठीक है जी। 2 to 3 वो जो होगा ना उस वक्त मोस्टली उनका होता है 2 to 3, पता नहीं अब क्या कर रहे होंगे। एक सेकंड यार, लेट मी सी द स्केड्यूल, क्योंकि लंच ब्रेक और प्रे ब्रेक मैंने देखनी है किस वक्त है। वो ये होता है कि दे कैन कॉल एनीवन, ठीक है, कि अपनी फाइल लेकर आए, उसमें से डेटा चेक करवाएं, तो हमने उस वक्त अवेलेबल रहना है। लंच ब्रेक, वो फाइल्स, दो से 3 लेक्चर करने की बजाय अगर हम 3 से 4 कर लें, उसे
ठीक है सर, फिर अगर 3 से 4 करना है, आप अगर फ्री हैं तो फिर उस वक्त कर लें।
तुम हो कहाँ पे इस वक्त? तुम्हें सांस चढ़ा हुआ
है? यस सर।
कहाँ पे हो?
सर मैं जरा थोड़ा बाहर था।
ठीक है, ठीक है
सर वो एक्चुअली मैंने डॉक्टर के पास विजिट करना था, तो इस वजह से ना मैं जरा बाहर आया हुआ।
लेक्चर साथ साथ ही चलेगा उधर?
सर वो अभी मैंने मोबाइल पे ज्वाइन किया है, तो एक्चुअली वो असल में
तो मैं आपको जो है ना 2 से 3 या 3 से 4, मैं आपको इन दोनों में से एक स्लॉट में आपका लेक्चर होगा कल, ठीक है? सो लेक्चर विल नॉट बी एट 10 o'clock, ठीक है? थैंक यू वेरी मच, एंड नाउ लेट्स स्टार्ट द लेक्चर. We have 32 students. I think we have sufficient number of students in the class. ठीक है जी, let me start the class. Rakib, the thing is, every day we have a meeting at 2:30. तो मेरा लेक्चर है आफ्टर 3 o'clock, तो मैं मीटिंग ज्वाइन करता हूँ आफ्टर 3. ठीक है, तो वो मीटिंग चलती है 2:30 to 4, तो वो फिर पूरी मीटिंग मिस नहीं की जा सकती, क्योंकि आजकल जो है वी आर डूइंग ऑल द एवरी डे वी हैव अ मीटिंग एट 2:30 होती है, तो वो फिर प्रेपरेशंस अपडेट करनी होती हैं, बताना होता है कि आपको जो काम असाइन हुआ है वेदर यू हैव कंप्लीटेड और नॉट, और फिर उसके ऊपर एवेल्युएशन होती है, वो फिर कमेंट्स मिलते हैं, यू नीड टू revise the work and then correct it. So that's why I cannot take 3 hours lecture today. आज एक ही होगा. ठीक है ज़ैम अली 001. Okay ji, Bismillahirrahmanirrahim. Let's start with our today's lecture. I hope everyone is fine. And our today's topic is strain transformation. So strain transformation is our chapter. It is chapter number 10 of R.C. Hibbeler 8th edition. And today we are first going to have the introduction about this chapter and what we are going to cover in this chapter. And then in the second half of the lecture, we will derive the equations for the computation of normal strains, shear strains, just like similar to the stress transformation which we had done earlier. So strain transformation, the transformation of strain at a point is similar to the transformation of the stress, and as a result the methods which we have studied in chapter 9, which was stress transformation, will be applicable to this chapter. In stress transformation chapter, if you recall, you have studied, you have first derived the equations to compute the transformed normal and shear stress. Then we solved the numericals. Then we have computed derived the equations for the computation of principal stresses, maximum in plane shear stresses, orientation of the principal stresses, orientation of the the shear planes. Fine. Then in the second half we studied the this Mohr circle. Fine. We then did some numericals related to the Mohr circle. So then we studied absolute maximum shear stress topic. So over here in chapter number 10, that is strain transformation, in this chapter we will follow the same. First we will derive the equations for the computation of transformed normal and normal strains and shear strains. Then we will derive the equations for the principal strains, orientation of the principal planes, maximum in plane shear strain, orientation of the shear planes. And then we will do some numericals. Then we will study the Mohr circle. Again we will solve some numericals. Then in the third part of this chapter we will study material property relationships. Material property relationships means that you have material property relationships is that, let's say, using the material properties like modulus of elasticity, modulus of rigidity, Poisson ratio, using these values, let's say I compute the stresses, I experimentally determine the stresses, and then using these relationships, I compute the strains. Or the thing is, if let's say you compute normal strain, you will compute, determine the normal strain, and from the formulas you will compute the shear strain. Then generalized Hooke's law is that you know that stress is directly proportional to the strain. So stress is equal to E times modulus times the strain. So in this case, what we will do, because we will develop the relationships for sigma x, sigma y, and sigma z, producing or correspondingly producing epsilon x, epsilon y, and epsilon z strains. Okay, ji? So we will derive some material property relationships and also what's the generalized Hooke's law equations. Okay, ji? At the very end of this chapter, there are four theories which we need to study. Two theories are related to what you say, failure of brittle material, and two theories are related to the failure of the ductile material. ठीक है जी, failure of brittle and ductile material. So at the very end we will study these four theories. So let's start first with the plane strain. So what is plane strain? Uh, First, they are defining the what you say simple definition that what is strain itself. So the general state of the strain at a point is represented by a combination of three components of normal strain and three components of shear strain. If you recall, strain is change in length over the original length. Strain is change in length. Strain is change in length over the original length. Okay? Now, the next thing is we have studied that there are two states. One is triaxial stress state we have studied, other was biaxial stress state. In triaxial stress state, or you can say general stress state, you had the normal stresses in sigma x in the form of sigma x, sigma y, and sigma z, and you have the shear stresses, ठीक है जी, tau xy, tau xz, and tau yz. Now, what will happen here that these normal stresses will produce normal strains. You can see this sigma x will produce basically epsilon x, sigma y will produce epsilon y, sigma z will produce epsilon z, and the shear stress will produce shear strain. So tau xy will produce gamma xy, tau xz will produce gamma xz, tau yz will produce gamma yz. ठीक है जी? So now if you just recall that in case of uh, triaxial stress state or general stress state, at each phase, let's say if you work in the on the x phase, on the x phase there is normal stress sigma x, and there are two shear stresses tau xy and tau xz. Similarly, on the y phase there will be normal stress sigma y, and there will be shear stresses tau yx and tau yz acting on the face y. Similar to this, on the face z, you will have uh, normal stress sigma z, and you will have shear stress tau zx and tau zy. And from there we concluded that there are basically three normal stresses, sigma x, sigma y, and sigma z, and there are three components of shear stress, because we said tau xy and tau yx they are same. Then we said that tau xz and tau zx they are same. Then we said that tau yz and tau zy they are same. ठीक है जी? So we concluded that in general stress state there are three normal stresses and three shear stresses. So similarly here, because we are working in elastic limits, so normal stress sigma x will produce normal strain epsilon x. Sigma y will produce normal strain epsilon y. Then sigma z will produce the normal strain epsilon z. and your shear stresses tau xy will produce shear strain gamma xy, tau xz will produce the shear strain gamma xz, and the shear stress tau yz will produce the shear strain gamma yz. These six components tend to deform each face of an element of the material, and like stress, the normal and the shear strain components, ठीक है जी, components at the point will vary according to the orientation of the element. So for a given, in the biaxial stress state, we said that we are just working in xy plane. On the x face, you have normal stress sigma x and the shear stress is tau xy. And on the y face, you have the normal stress sigma y and the shear stress is tau yx. We said that tau xy and tau yx, they are same. ठीक है जी, so we had two normal stresses in our plane state of the stress, two normal stresses sigma x sigma y and one shear stress tau xy. ठीक है जी. Now in the case of what you say biaxial state, or you can say plane state of the strain, in that case you will have two normal strains epsilon x and epsilon y, and you will have one shear strain gamma xy. Now in for any given element, sigma x, sigma y, and gamma xy, they will remain the same. So with the change in the theta, so with the change in the orientation of the element, your transformed normal and the shear strains, your transformed normal and the shear strains, they will vary. ठीक है जी. So with change in theta, your epsilon x dash, epsilon y dash, and gamma x dash y dash over 2, it will vary. And today we will derive the equations for the computation of transformed normal strain, that is epsilon x dash and epsilon y dash, and transformed shear strain, that is gamma x dash y dash over 2. ठीक है जी. The strains at a point are often determined by strain gauges, which measure normal strains in the specified direction. Now, the important point to remember over here is that in case you attach the strain gauges, ठीक है जी, now you know that when you will have a tension test, when you will pull the steel bar, ठीक है जी, what will happen? Tensile stresses will produce the tensile strains, ठीक है जी, along the longitudinal direction. You can say you will get the longitudinal strains in the steel bar. But in the perpendicular direction, due to Poisson's effect, we know that lateral strains will be produced, which will be in opposite direction to the longitudinal strains, and that will result in the reduction in the dia of your steel bar. ठीक है जी. Now basically due to the Poisson's effect, normal strains are also produced, but in strain gauges, the strain gauges which you will use, they will only measure the strains in the normal direction. They will not be able to measure the lateral strain. So if you measure the normal strains, then the lateral strains we can compute using the formula minus sign the Poisson ratio into the longitudinal strain. For both analysis and design, however, engineers must sometimes transform this data in order to obtain the strain in other direction. To obtain the strain in other direction. Is this point clear? Guys, how many of you are aware of the Poisson's effect? If you are clear about the Poisson's effect, let me know. If you are not aware of this effect, how it works, ask me so that I can draw the figure and explain to you. Because yesterday I had class, I think with C section, they were not aware that how the Poisson's effect works. And I think so जो आप लोग बोल नहीं ना रहे. ठीक है जी, this is your steel bar and this is the tensile stress which you have applied. ठीक है जी, which will result in the elongation of the element. ठीक है जी, this is now your steel bar. So what will happen when you will pull the steel bar? You know that along the longitudinal direction, this is your longitudinal axis. क्या होता है? Axis along the length of the element. This is your steel bar. This is the length. So longitudinal axis will be along the length of the element. So this stresses will be basically passing through the longitudinal axis. So now what will happen? After the tensile test, you know that your length of the steel bar will increase. However, the dia of the steel bar reduces. Why? जी बताएं. You can see now I have shown that the length of the steel bar has increased. However, your dia has reduced. ठीक है जी, this is the new dia. Original dia was this one. So the dia of the steel bar has reduced. जी.
सर आपकी स्क्रीन शेयर नहीं हो रही है इन केस अगर आप शेयर करें.
Screen is shared from my side. Screen is shared from my side. I don't know. From my side it is shared. So your longitudinal strain, this longitudinal strain, let's say you have attached a strain gauge. ठीक है जी, you have attached a strain gauge like this. ठीक है जी. Now this strain gauge attached in the longitudinal direction, it will measure the longitudinal strain. ठीक है जी, let's say you have longitudinal strain. Otherwise you know that strain क्या होगा. ठीक है जी, either you can get it from the strain gauge or you can say change in length delta L over the original length. ठीक है जी, change in length over the original length. Change in length over the original length. You can calculate the longitudinal strain, but if you have attached the strain gauge along the longitudinal direction, it will give you the longitudinal strain. Now the lateral strains which are in opposite direction to the longitudinal strains. ठीक है जी, transverse strains or your lateral strains. transverse strains or your lateral strains which are in opposite direction, ठीक है जी, which are in opposite direction to your longitudinal strains, this strain gauge will not measure them. ठीक है जी, because this strain gauge is attached in longitudinal direction, it will only measure longitudinal strain. So transverse strain I will calculate using the Poisson's ratio. So transverse strains, which are the strains perpendicular to the longitudinal direction, so these strains will be opposite in sign or opposite in direction to the longitudinal strain. So this is the negative sign to show the opposite direction. This is not V, actually this is mu. This is your Poisson's ratio. Poisson's ratio for the steel is 0.3. Longitudinal strain, which is this one which you have measured with the strain gauge. So you can measure the transverse strain in this way. Okay? Not measure, you will compute the transverse strain in this way. Poisson's ratio is a material property, and Poisson ratio value will vary for different elements. Like for the steel, it is 0.3. For the concrete, it varies from 0.15 to 0.2. For FRPs, the value is close to 0.2. For different materials, different Poisson's ratio values. Okay? So your strain gauge will only measure the strain in the direction in which it is attached. Okay? Now, interesting thing is that due to the Poisson's effect, a lateral strain is produced. Okay? Everyone agree to this point? Okay. Now let's discuss the plane strain. Plane strain. Now you see this is three-dimensional element. Moin, can you see this figure?
Yes, sir.
So you can see this three-dimensional element X, Y, and Z. There are two stresses because in case of the plane state of the stress, we say that there is only sigma X and sigma Y. Okay, ji? Now in the plane strain, I have told you earlier, there should be only epsilon X and there should only be epsilon Y. There should not be epsilon Z because there is no stress applied in the Z direction. So see what happens. Sigma X will produce the normal strain epsilon X. Okay? But due to Poisson's effect, there will be lateral strain in Y and Z direction due to this longitudinal stress in X direction, producing longitudinal strain in X direction, epsilon X. Okay? So a lateral strain in Y direction and Z direction will be produced. Okay? Similarly, sigma Y, a normal stress is acting along the Y direction, so it will produce a normal strain epsilon Y. It will produce a normal strain epsilon Y. Okay? Now, due to the Poisson's effect, this normal strain epsilon Y will produce epsilon X, a component in X direction and a component in Z direction. Now the problem comes. Problem comes that you have only stresses in sigma X and sigma Y, but you have strains in Z direction. ठीक है जी. You have the strain in z direction due to the Poisson's effect because both these normal strains epsilon x and epsilon y will have a component of the strain in z direction due to Poisson's effect. ठीक है जी. Due to Poisson's effect, this will have the effect in z direction. No, this is not over plane strain. This condition is not over plane strain condition. Reason is you have epsilon z now. To understand how this is done, we will first confine our attention to a study of plane strain. Specifically, we will not consider the effects of the components epsilon z, gamma xy, xz, and gamma yz. We agree to this because in biaxial stress state, we have studied that sigma z is not there and the shear stress tau xz and tau yz, they are not there. ठीक है जी. So in general, then a plane strained element is subjected to two components of normal strain, epsilon x and epsilon y. So sigma x will correspond to epsilon x, sigma y will basically correspond to epsilon y, and one component of the shear strain, that is gamma xy. So in your plane state or plane strain state, you have epsilon x, epsilon y, and gamma xy. ठीक है जी. Just like in case of the plane stress, where you had sigma x, sigma y, and tau xy. ठीक है जी. So in plane strained element, you will have now epsilon x, epsilon y, and shear strain. ठीक है जी. Now at present I have told you there is epsilon z as well. Now this is making a problem that this is not a plane strain example. Although plane strain and plane stress each have three components lying in the same plane, realize that plane stress does not necessarily cause plane strain. Please note down this point. I have explained to you that sigma x, sigma y, ठीक है जी, two normal stresses, they are producing three normal strains, epsilon x, epsilon y, and epsilon z. So plane stress does not necessarily produce plane strain scenario. The reason for this has to do with the Poisson's effect. ठीक है? Poisson's effect. ठीक है? If the element in this figure is subjected to plane stress sigma x and sigma y, not only the normal strains epsilon x and epsilon y are produced, but there is also a normal strain, associated normal strain epsilon z is produced. ठीक है जी? So if the element is subjected to plane stress, sigma x and sigma y, not only are normal strains epsilon x and epsilon y are produced, but there is also an associated normal strain epsilon z is produced. ठीक है जी? This is obviously not a case of plane strain. ठीक है? In general, ठीक है, unless we assume that the Poisson's effect is zero. So what will happen if I assume Poisson's effect is zero? Normal stress sigma x will only produce the strain epsilon x. It will not produce the lateral strain in y direction and lateral strain in z direction. Similarly, normal stress sigma y will only produce normal strain epsilon y. It will not produce a lateral strain in x and z direction. ठीक है जी? So in general, unless Poisson's effect is taken zero, the Poisson effect will prevent the simultaneous occurrence of plane strain and plane stress. Now, in case of plane strain case, we are assuming that the Poisson effect is zero. So sigma x will only produce epsilon x and sigma y will only produce epsilon y. Is this clear? If you have any query, please ask me now. Okay, if no question, then we are proceeding further. General equations of plane strain transformation. It is important in the plane strain analysis to establish the transform equations that can be used to determine x dash, y dash, components of normal and shear strain at a point, provided the xy components of strain are known. Of course, if you are given plane strain scenario in which epsilon x, epsilon y, and gamma xy are given, you can calculate the transformed normal strains epsilon x dash, epsilon y dash, and gamma x dash y dash as a function of theta. ठीक है जी. So essentially this problem is one of geometry and requires relating the deformations and rotations of the line segments which represent the sides of different elements that are parallel to each set of axes. Now the sign convention. In the stress transformation, we have said that tensile stresses, they are considered positive. Tensile stresses, they are considered positive as tensile strains, they will produce, tensile stresses will produce tensile strains, and tensile strains will produce or will basically result in the elongation of the element. So, before the strain transformation equations can be developed, we first establish a sign convention for the strains. So, with reference to the differential element, this one shown in the figure 10 to 8, normal strains epsilon x and epsilon y are considered positive if they cause elongation along the x and y axis respectively. ठीक है जी? Agree with this point? So just like tensile stresses were positive and compressive stresses were considered negative. So similarly here, tensile strains will be considered positive as they will produce the elongation in the element, and what you say, compressive strains which will produce the contraction in the element, they will be considered as negative. They will be considered as negative. Fine. So epsilon x and epsilon y are positive if they cause elongation along the x and y axis respectively. And the shear strain is positive if the interior angle AOB becomes smaller than 90 degrees. That I will explain to you now. So this is our element. This is our element. ठीक है जी, solid element AOB with the dimension, original dimension dx and dy. ठीक है जी. This dotted line, this dotted lines, these are the distorted shape of the element after the tensile stresses acted on the element. So due to the tensile stresses, what happened? You have elongation. ठीक है जी? You have elongation along the x direction. We know that strain is change in length over the original length. Strain is change in length over the original length. Now strain is epsilon x, original length is dx. So change in length is epsilon x times dx. ठीक है जी? And this dy, now the strain in the y direction, it has resulted in the change in length in the y direction. So change in length is strain times the original length. So strain is epsilon y, original length is dy. So change in length is epsilon y times dy. Epsilon y times dy. So this is now your strain or change in length in the y direction. And you can see this, there is an increase in the length of the element along the y axis and along the x axis. Along the y and along the x axis, there is increase in the length. Epsilon y dy, you can see there is a positive change in the length, which means there is elongation in the length along y axis. Again, you can see increase in length, positive epsilon x dx. So there is increase in the length about x-axis and y-axis. So normal strains, tensile stresses produce tensile strains which result in the elongation of the element about x and y-axis. Any questions about this normal strains? Sign convention about the normal strains. Sign convention for the normal strain. Sign convention for the normal strain. Now, next thing is we have to what you say, uh, study the sign convention of the shear strains. So what are the shear strains? Sign convention. So we have said that originally this angle AOB, was 90 degrees. Okay, AOB was 90 degrees. Fine. Now, after the application of the tensile stresses, or you can say corresponding tensile strains are produced, this distorted element, okay, you can see this angle AOB has reduced. So shear strain is gamma xy. Shear strain is gamma xy over 2. Okay, this is the reduction in the angle from AO side. This is reduction in the angle from OB side. So reduced angle is this one. So sign convention is that shear strain gamma xy, shear strain gamma xy is positive if the interior angle AOB becomes smaller than 90 degrees. ठीक है जी? Shear strain gamma xy is positive if the interior angle AOB becomes smaller than 90 degrees. And if this angle AOB becomes greater than 90 degrees, it is negative shear strain, and that will result when there will be contraction. The sides, their size will reduce and this angle will increase. So the sign convention also follows the corresponding one used for the plane stress. One thing more before proceeding further, the sign convention for the theta. Earlier we have said that if we curl the fingers of the right hand moving from x to x dash direction, curling the fingers from x to x dash direction, then your thumb will point. Uh, if the thumb points out of the plane, that is theta is counterclockwise, it is considered positive. And while curling the fingers, let's say if x dash axis is downwards, moving from x to x dash direction, what will happen? Your thumb will point into the plane. When your thumb will point into the plane, thumb will point into the plane, it will be considered as clockwise, and clockwise is considered negative. So sign convention for theta is the same, and for the normal and the shear strength is based on the normal and the shear stress sign convention. So now one more thing to be noted, sigma x will produce epsilon x because only will produce epsilon x because Poisson's effect is 0. Sigma y will produce epsilon y only because Poisson's effect is 0. Shear stress tau xy will only produce gamma xy. The problem here will be to determine at a point the normal and the shear strains. The normal and the shear strains epsilon x dash, epsilon y dash, gamma x dash y dash, which are measured relative to the x and x dash y dash axis. If we know the plane state of the strain, if we know the plane state of the strain, that is epsilon x, epsilon y, and gamma xy, which we will measure relative to the x and y axis. If the angle between the x and x dash axis like this, it is theta positive because this is counterclockwise. Then, like the case of the plane stress, theta will be positive provided it follows the curl of the right hand fingers counterclockwise as shown in this figure. ठीक है जी, counterclockwise theta is positive, clockwise theta is negative. Any questions up to this point? Any questions? If no questions, then we will have a short break of 10 minutes. ठीक है जी? And after the break, we will start with the derivation. So do bring your pencils and registers to do the derivation. Guys, are you back?
Yes, sir.
Please take out your copies and pencils so that we can start the derivation. Okay, Ji, Bismillahirrahmanirrahim, let's start the derivation. So, normal and the shear strains. Now, first of all, try to understand the figures. So, this is your element. Okay, this one is your element. Its dimension about the x-axis is dx. Its dimension about the y-axis is dy. So this is dx, this is dy. Along the x-axis you have dx, along the y-axis you have dy. Now your element has rotated by an angle theta. So this is now your new position of x dash axis, and this is your new position of y dash axis. This is your dx dash, the length of the element about the x dash axis. So in order to develop the strain transformation equation for epsilon x, so we are going to derive the equation for the strain transformation equation for epsilon x dash. So we are going to derive the equation for the strain transformation equation epsilon x dash. So we must determine the elongation of the line segment dx. So we want to determine the elongation of this line segment dx dash, which is along the x dash axis. So we must determine the elongation of the line segment dx dash that lies along the x dash axis and is subjected to the strain components, epsilon x, epsilon y, and gamma xy. This epsilon x, epsilon y, and gamma xy, these are your plane state of the plane strain. This is your state of the plane strain. Fine. So as shown in the figure 10.3a, in the figure 10.3a, the components of the line dx dash along the x and y axis are. So this is your dx dash. We want to calculate its component of this line dx dash about x axis and about y axis. Why? Because our plane state of the strain, that is normal strains and shear strain, they are oriented about x and y axis. So we need to calculate the strain transformation about x dash axis. आपको calculate about x dash axis करना है, whereas your strains are about x and y axis. So that's why we need to find the component of this line dx dash about x and y axis. So we need to find the component of dx dash about x and y axis. So in order to develop the strain transformation equation for epsilon x dash, we must determine the elongation of the line segment dx dash that lies along the x dash axis and is subjected to the strain component epsilon x, epsilon y, and gamma xy. As shown in figure 10.3a, the components of the line dx dash, the components of the line dx dash along the x and the y axis. ठीक है जी, the components of the line dx dash along the x and the y axis are. So dx is dx dash cos theta, and this along the y dy is dx dash sine theta. So simple trigonometry. This is this is base, this is perpendicular, this is hypotenuse, this is theta. So dx is equal to dx dash cos theta. dy is equal to dx dash sine theta. ठीक है जी, everyone agrees to this point? Everyone agrees to this point? So next is when the positive normal strain epsilon x occurs. ठीक है जी, when the positive normal strain epsilon x occurs, the line dx is elongated. So now on this we want to calculate, ठीक है जी, the influence of these normal strains epsilon x, epsilon y, and the shear strain gamma xy on the line dx dash, on the line dx dash. So when the positive normal strain, when the positive normal strain epsilon x occurs, ठीक है जी, now you can see this is your dx, the original dimension of the line along x-axis is dx. ठीक है जी, strain is epsilon x, so change in length is strain times the original length. So change in length is epsilon x dx, and you can see this, there is increase in the length about the x-axis. There is increase in the length about x-axis, and that increase is epsilon x dx. ठीक है जी, now you can see this is epsilon x dx, and we will determine its two components about x dash axis and y dash axis, because this change in length due to the normal strain epsilon x is in x direction. So we need to find the component of this epsilon x dx in x dash direction and y dash direction. ठीक है जी, in x dash direction and y dash direction. ठीक है जी, so in the x dash direction you have the component epsilon x dx cos theta, and about the y dash the component is epsilon x dx sin theta. ठीक है जी, so about the y dash, about the y dash axis, the component is epsilon x dx sine theta. Any questions? Any questions? Epsilon x dx is hypotenuse, this is the base, this is the perpendicular, this is your theta. ठीक है जी, so you can find the components. This is epsilon x dx, so this component will be base, epsilon x dx cos theta, this is perpendicular, epsilon x dx sine theta. ठीक है जी, now you have another is epsilon y. ठीक है जी, epsilon y. So epsilon y will result in change in the strain along the y direction. ठीक है जी, so the original length is dy and the sign is strain is epsilon y. So change in the length will be, change in the length will be normal strain epsilon y times the original length dy. So the change in strain is epsilon y dy, epsilon y dy. ठीक है जी, now this change in length epsilon y dy is along the y axis. this is along the y-axis. So its component about the x dash axis will be epsilon y dy sine theta, and about x dash axis will be epsilon y dy sine theta, and about the y dash axis it will be epsilon y dy cos theta. Guys, just a moment. So now you can see this is your hypotenuse, this is base, this is perpendicular. So this is epsilon y dy sine theta, this is epsilon y dy cos theta. Now you can please note down one more thing, that this epsilon y dy cos theta component is pointing towards positive y axis. So this will be positive epsilon y dy cos theta. This epsilon y dy sin theta is pointing towards positive x-axis. ठीक है जी? Epsilon y dy sin theta is pointing towards the positive x-axis. ठीक है जी? So this is epsilon y dy sin theta. ठीक है? Positive. Over here, epsilon x dx cos theta was pointing towards positive x dash axis, so that was positive, and epsilon x dx sin theta, that was pointing downwards towards the negative y dash axis, so this was negative epsilon x dx sin theta. ठीक है जी? Now next is the influence of gamma xy. As we have said earlier, that the shear strain is the change in angle AOB. ठीक है जी? If you see this, I can show you again this figure. Shear strain is change in the angle. If the change in the angle AOB is like becomes smaller than 90 degrees, then the shear strain is positive. If it is greater, if that angle AOB becomes greater than 90 degrees, then the shear strain is negative. So now let's see the influence of gamma xy. This figure, this one. This is dy, this is dx. ठीक है जी? We have said that the shear strain is change in the angle. So over here, what we have done, that we have fixed this length dx, means to say that angle of dx, it will not change. However, upon the application of the shear strain, what has happened, that this dy has moved to this point. ठीक है जी? The dy, ठीक है जी, dy has moved to this point, that is new point, you can say. Now this change in the length from this point to this point, that is change in the length, that is gamma xy, the shear strain times the original length dy. So change in length is gamma xy dy. Now, if we want to find the components of gamma xy dy about x dash axis, that is this component, that is gamma xy dy cos theta, and it is pointing towards positive x-axis, so it is positive, and this gamma xy dy vertical component about y dash axis is this one, gamma xy dy sin theta, and it is pointing towards negative y dash axis, so it is gamma xy dy sin theta. ठीक है जी? Now you have seen that the strains epsilon x, epsilon y, and gamma xy will produce the change in the length. ठीक है जी? And correspondingly, we have found the component of the change in the length about x dash axis and y dash axis. ठीक है जी? Now let's read from the book. When the positive normal strain epsilon x occurs, epsilon x occurs, the line dx is elongated by epsilon x dx, which causes the line dx dash to elongate by this much, epsilon x dx cos theta. ठीक है जी. Likewise, when the normal strain epsilon y occurs, line dy is elongated. ठीक है जी. Line dy is elongated to new length epsilon y dy. Now, which causes the line dx dash to elongate epsilon y dy sin theta. Finally, assuming for the shear strain now. Finally, assuming that the dx remains fixed in position, the shear strain gamma xy, which is the change in the angle between dx and dy, causes the top of the line dy to be displaced. So this is dx, this is dy, this is the new position of dy, and this is the change in the length gamma xy dy. So its component about the x dash axis is this one, gamma xy dy cos theta. So this causes dx dash to elongate by gamma xy dy cos theta. If we add all these three elongations are added together, the resultant elongation of the line dx dash, the resultant elongation of the line dx dash is, ठीक है जी. Now, what is the change in the length or increase in the length represented by delta x dash? So, due to the strain epsilon x, the increase in the length about x dash axis is epsilon x dx cos theta. So, epsilon x dx cos theta. And increase in length due to the normal strain epsilon y, the increase in length about the x dash axis is epsilon y dy sin theta. And due to the shear strain gamma xy, the increase in the length about the x dash axis is gamma xy dy cos theta. Gamma xy dy cos theta. So delta x dash, the elongation in the line, the elongation of the line dx dash is delta x dash, which is equal to epsilon x dx cos theta plus epsilon y dy sin theta plus gamma xy dy cos theta. If you have any questions, please let me know. So, वैसे आपका जो सेक्शन है ना, मुझे सबसे ज्यादा वैसे अजीब से लगता है. You guys do not respond B section. बाकी सारे सेक्शन रिस्पॉन्ड करते हैं, आप लोग कोई रिस्पॉन्ड नहीं करते. तो वैसे आप लोगों को जो क्लास पार्टिसिपेशन है ना, आई विल गिव यू 0 मार्क्स इन दैट. वो आपका बनता भी 0 ही है. पता नहीं सोए हुए हैं, क्या कर रहे हैं. नो, आपको एक्सप्लेन करने की जरूरत नहीं. Now, this is the elongation delta x dash of the line dx dash. ठीक है जी. Now, the normal strain along the line dx dash is epsilon x dash is equal to delta x dash over dx dash. So this is over strain. ठीक है जी. So epsilon x dash is the strain about the line x dash axis. ठीक है जी. So delta x is the change in the length over the original length. So change in length is delta x dash, which is sum of the elongations due to epsilon x, epsilon y, and gamma x y. ठीक है जी. So the normal strain along the line dx dash is epsilon x dash is equal to delta x dash over dx dash. So now in this equation, you will put the in this equation, because we want to find the expression for epsilon x dash, in this equation we will put the value of delta x dash and we will divide it by dx dash. Along with that, you have to do one thing, that dx is dx dash cos theta and dy is dx dash sin theta. So you have to put these values of dx and dy in the equation as well. ठीक है जी, यहाँ पे dx is यहाँ पे dx और dy their values will be coming from here. Dx is dx dash cos theta, dy is equal to dx dash sin theta. ठीक है जी. So after simplification you will get this expression, epsilon x is equal to epsilon x cos square theta plus epsilon y sin square theta plus gamma xy sin theta cos theta. Now in this equation, now in that equation you will put the identities, trigonometric identities. Sin theta is equal to 2 sin theta cos theta, cos square theta is this one and sin square theta is this one. Sin square theta plus cos square theta is 1. So you will get this final expression. ठीक है जी. Epsilon x dash is equal to epsilon x plus epsilon y over 2 plus epsilon x minus epsilon y over 2 cos 2 theta plus gamma xy over 2 sine 2 theta. So this is your expression, finalized expression for the computation of epsilon x dash. Then to find the what you say expression for epsilon y dash, to find the expression for epsilon y dash, ठीक है जी, we will just simply in this equation 10(5) to get the expression for epsilon y dash. What we will do in this equation, we will replace theta with 2 theta, theta with theta plus 90, theta plus 90, because x dash and y dash axis, they are oriented at 90 degrees apart. So to get the expression for epsilon y dash, you will just put the value of theta in this equation as theta plus 90 and you will get the expression for epsilon y dash, that is equal to epsilon x plus epsilon y over 2 minus epsilon x minus epsilon y over 2 cos 2 theta minus gamma xy over 2 sine 2 theta. Now next we are going to do the expression for the shear strain. Shear strain. I will quickly go through because you guys do not take any interest in the class, so there is no point in giving you very much detail. You should study yourself as well something. So next is the strain transformation for gamma x dash y dash. Okay, so epsilon x dash we have it. So now the strain transformation equation for gamma x dash y dash can be developed by considering the amount of rotation each of the line segment dx dash and dy dash undergoes when subjected to the strain component epsilon x, epsilon y, and gamma xy. So this is your x dash. So this is dx dash. We have already computed the elongation of the line dx dash, that is delta x dash. Okay, now this dx dash is rotated by an angle alpha. So this is the new position of dx dash. Similarly, dy dash is rotated by an angle beta, and this is its new position dy dash. Now what we have to do, we know that alpha, if we just use simple trigonometry, tan alpha is equal to delta y dash over dx dash, and we know that for small angles tan theta will be equal to theta. So this for small angles, alpha will be equal to tan alpha. So this will become alpha is equal to delta y dash over dx dash. So that strain transformation equation for gamma x dash y dash can be developed by considering the amount of rotation each of the line segment dx dash and dy dash undergo when subjected to the strain component. So first we will consider the rotation of dx dash, which is defined by the counterclockwise angle alpha. ठीक है जी, as shown in this figure, this alpha we are defining. So it can be determined by the displacement caused by delta y dash. It can be determined by the displacement caused by delta y dash. So we want to calculate this deformation caused by delta y dash. We know that alpha is equal to delta y dash because this is your base. Sorry, this is your perpendicular and this is your base. So alpha is equal to delta y dash over dx dash. So we need to calculate delta y dash. ठीक है जी, if you recall, we have already calculated delta x dash. ठीक है जी, which were the sum of the deformations about the x dash axis due to epsilon x, epsilon y, and gamma xy. So here we will calculate the deformations about the y dash axis, that is delta y dash, due to epsilon strain component, epsilon x, epsilon y, and gamma xy. ठीक है जी. So to obtain delta y dash, the deformation delta y dash, uh, to obtain the deformation delta y dash, ठीक है जी, we will consider the following three displacement components acting in the y direction. One is epsilon x, ठीक है, one from epsilon x, another from epsilon y, and the third one is be from gamma xy. Let me show you again. Now, this one, epsilon x dx, the deformation along the x-axis has the, due to the strain epsilon x has the component, this one, epsilon x dx sine theta, ठीक है जी, epsilon x dx sine theta, and this epsilon x dx sine theta is the deformation along the y dash axis, ठीक है जी, perpendicular, and it is acting downwards, so it is negative. So this will be negative epsilon x dx sine theta. Then you have, due to epsilon y, you have the deformation, this one, epsilon y dy cos theta. You have the deformation epsilon y dy cos theta, and it is pointing towards the positive y axis, so it is positive. So this value will be positive epsilon y dy cos theta. ठीक है जी. Then the third one, due to the shear strain, then the third one due to the shear strain is this one, gamma xy dy sin theta, which is parallel to the y dash axis, and this is pointing downward. So this is now negative gamma xy dy sin theta. No. So to obtain delta y dash, consider the following three displacement components acting in the y direction. One from epsilon x, ठीक है जी, that is minus epsilon x dx sin theta. Another from epsilon y, which gave us epsilon y dy cos theta. And the third one is from this shear strain, which gave us negative gamma xy dy sin theta. So thus delta y dash is the sum of all the three strain components, that is minus epsilon x dx sin theta plus epsilon y dy cos theta minus gamma xy dy sin theta. If you have any question, you can ask me now. No question. So alpha is equal to we know that alpha is equal to delta y dash over dx dash. Delta y dash is this one, minus epsilon x dx sin theta plus epsilon y dy cos theta minus gamma xy dy sin theta divided by dx dash. In this again dx dy, their values you are going to put these ones. Dx is equal to dx dash cos theta dy is equal to dx dash sin theta. ठीक है जी?
Yes, sir.
So after simplification, alpha is equal to delta y dash over dx dash. After simplification, you will get alpha as equal to minus epsilon x plus epsilon y times sine theta cos theta minus gamma xy sine square theta. Okay. Now, as earlier in the figure, this one we have seen that over dx dash has rotated by an angle alpha and dy dash is rotated by an angle beta. Okay. So alpha we have computed. Now we need to compute beta. We know that the difference between these two will be 90 degrees. You can see this x dash and y dash, the difference between these two axes will be 90 degrees. Okay. Now the line dy dash rotates by an amount beta. We can determine this angle by a similar analysis or by just simply substituting theta plus 90 for theta in equation 10(3). So in this equation 10(3), we can place theta plus 90 as a substitute for the theta. ठीक है जी? So now in this equation, beta will be equal to, you can see, minus epsilon x plus epsilon y sine theta plus 90 cos theta plus 90 minus minus gamma xy minus gamma xy sine square theta plus 90. ठीक है जी? You will simplify this equation. You will simplify this equation and you can use the following identities, that sine theta plus 90 is cos theta, whereas cos theta plus 90 is equal to minus sine theta. ठीक है जी? So you will use these identities and then after simplification, you will get beta as this one, minus bracket minus epsilon x plus epsilon y cos theta sine theta minus gamma xy cos square theta. So now we know that since alpha and beta represents the rotations of the side dx dash and dy dash of the originally rotated element. You can see this alpha represents the rotation of dx dash. Beta represents the rotation of dy dash. ठीक है जी? Alpha represents the rotation of dx dash. Beta represents the rotation of dy dash. So since alpha and beta represents the rotations of the sides dx dash and dy dash of a differential element whose sides were originally oriented along the x and y dash axis. ठीक है जी? Now we know that the shear strain is the reduction in the angle. ठीक है जी? Reduction in the angle AOB. So the transformed shear strain will be alpha minus beta. ठीक है जी? So your shear strain will be, this is x dash axis, this is y dash axis. So the difference in the angle alpha and beta will be your shear strain, the angle by which your element has distorted. ठीक है जी? So alpha minus beta. ठीक है? This angle we have taken between new position of dx dash and earlier older position of dy dash as 90 degrees. ठीक है जी? So difference between alpha and beta will be your shear strain, transformed shear strain. So gamma x dash y dash, so gamma x dash y dash is equal to alpha minus beta, and you have the value of alpha as minus epsilon x plus epsilon y times sine theta cos theta minus gamma xy sine squared theta, whereas beta is equal to minus, that is bracket minus epsilon x plus epsilon y cos theta sine theta minus gamma xy cos squared theta. So your shear strain is, transformed shear strain is gamma x dash y dash is equal to alpha minus beta. You will put the value of alpha and beta here, and then you will simplify and you will get these equations. Then at the end in that equation, you will put the trigonometric identities. Sine 2 theta is equal to 2 sine theta cos theta, whereas cos square theta is 1 plus cos 2 theta over 2, and sine square theta plus cos square theta is 1. So after simplification, you will get this equation, that is gamma x dash y dash over 2 is equal to minus epsilon x minus epsilon y over 2 sine 2 theta plus gamma xy over 2 cos 2 theta. Now, if you see these equations, they are exactly similar to the stress transformation equation, where sigma x corresponds to epsilon x here, sigma y corresponds to epsilon y here, and shear stress tau xy corresponds to gamma xy over 2 here. When you will simplify these equations, you will find out that in these equations, there is a factor of 2, which basically means that tau xy, shear stress tau xy corresponds to shear strain gamma xy over 2. Shear stress tau xy corresponds to shear strain gamma xy over 2. These strain transformation equations gives the normal strain epsilon x in the x dash direction and the shear strain gamma x dash y dash of an element oriented at an angle theta. So according to the established sign convention, epsilon x is positive, the element elongates in the positive x direction, and gamma x dash y dash is positive if the element deforms in the way that your angle is reduced. This we have already done, that to get the epsilon y dash expression, we can just simply replace theta with theta plus 90 in epsilon x dash equation, and after simplification we will get the equation for epsilon y dash is equal to epsilon x plus epsilon y over 2 minus epsilon x minus epsilon y over 2 cos 2 theta minus gamma xy sine 2 theta. So next thing which we have to study, that is the similarity between the above equations, which we have derived from the transformed normal and the shear transformed normal and shear strains, that they are exactly similar to the plane stress equations. ठीक है जी? Sigma x corresponds to epsilon x because there is no Poisson's ratio. Sigma x corresponds to epsilon x. Sigma y corresponds to epsilon y. Sigma x dash corresponds to epsilon x dash. Sigma y dash corresponds to epsilon y dash. Tau xy corresponds to gamma xy over 2, and tau x dash y dash corresponds to gamma x dash y dash over 2. ठीक है जी? If you have any question, ask me now. Otherwise, that's it for today. Okay, thank you very much.